Hello, Hire, and welcome to the energy profiles lesson. This is the second part of the rates and energy profiles lessons. Last week we had a wee look at controlling the rates, which was mainly Nat 5 division. This is where we're really going to get into the higher part of this subtopic. This is, of course, a subtopic of Unit 3, which is Chemistry and Society. So for the energy profiles lesson, we are going to investigate the chemistry behind reactions. We're going to do that by taking a look at something called activation energy and enthalpy, which you already know a little about, but we're going to go into that in much more detail. Our success criteria for this lesson is to define activation energy, the activated complex, and show an understanding of these by annotating graphs and also being able to answer questions correctly, of course. So let's jump in. Activation energy, first of all. Remember, temperature is a measure of the average kinetic energy of the particles in a substance. The higher the temperature, the larger the kinetic energy of the particles, so the faster they're moving around, etc. The activation energy, now this is your definition that I'd like to copy down and highlight. The activation energy is the minimum energy required for a reaction to occur. So when we're talking about molecules, particles in a reaction having the right amount of energy, that is what we mean. We mean this activation energy. That's the minimum energy required for a reaction to occur. So that means that reactant molecules have enough kinetic energy to collide successfully and overcome the repulsion caused by outer electrons. Remember, bringing in all of your chemistry knowledge so far from this, there are electrons which are moving around the outside of individual atoms. For those atoms to collide, they do have to overcome that repulsive force between the two like-charged negative electrons. So here is what a typical graph looks like to show the kinetic energy of particles. Now this is a normal distribution curve, which basically very simply means that in this part here, there are very little molecules. If we just shade this area of the graph here, there are very little numbers of molecules that have low kinetic energy. And similarly, there are very low numbers, if we just shade in this area of the graph here, very little numbers of molecules with high kinetic energy. This is called a normal distribution because the majority of the molecules are in this middle section here, where they have a kind of middle of the road kinetic energy. It's not too low, it's not too high. It's kind of like a Goldilocks thing, if you remember the story. But that is just showing you, we're going to look at a lot of these different graphs, and that is where this graph comes from. So it's the number of molecules versus the kinetic energy. There are lots of different examples of this type of graph. Example number 1, now I want you to annotate these in your notes book the way I am annotating them right now. And the first example we have is temperature. So we want to have a think about, well, how might temperature affect this distribution here? Well, as I said before, we have number of molecules and kinetic energy. So if we just think about this logically, if we increase the temperature of our reaction, then we know already that the particles are going to have more kinetic energy and they're going to be able to collide much faster. So if, for example, we say this is temperature 1, and we want to know what will this graph look like if we decrease the temperature. So we're going to call that temperature T2. What that means is there are going to be more or higher numbers of molecules which have an increased kinetic energy. So the curve is not going to be so center focused in the middle. What we're going to have to do is we're going to have to shift it to the right a little bit. Now, if more molecules have a higher kinetic energy, then the curve, that means, is going to have to flatten a little bit. So I'm going to show you how I would draw this. I would draw it lower and to the right hand side. Hopefully you can see that colour of pen. So that would be temperature 2, which would be a lower temperature. Sometimes they give you the lower temperature and ask you what the curve would look like at a higher temperature, and you would of course then just make the curve more narrow and pull it back to the left a little bit. But most of the time they're giving you a temperature and asking you what an increase in temperature would look like. Now, if we said, for example, that our activation energy was here, where this line is. So this is the line, and everything over this line has enough energy to react. But we can have a little look at what these curves actually are telling us about those number of molecules. First of all, at the lower temperature, the area under the graph is this area here. And that is not a substantial amount of area. It's quite a small number of molecules that have that kinetic energy to collide successfully. Whereas if we look at our higher temperature curve, which is this one here, we have all of this area. All of that area represents a much, 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 much larger number of molecules that have the sufficient kinetic energy to collide successfully. So that is how temperature affects this distribution here regarding the activation energy. The second example we have here is concentration. And again, we're just going to take a very logical approach to this and think to ourselves, if we are to double the concentration, there is going to be double the number of molecules in our solution. So it makes sense that our number of molecules is going to go up. Therefore, our graph is going to look something like that. Now, the graph isn't moving up or down because when we alter the concentration of solutions, we're not actually doing anything to the kinetic energy. It's not like we're increasing or decreasing it. The only thing we are increasing is the number of molecules. But again, if we have a look at how this affects the activation energy, let's do that in a different colour. Then if the activation energy was where this green line is that I have not drawn greatly, then if we look at the lower concentration, our area of the graph is only this big. So this is the number of molecules that have that kinetic energy to successfully collide. If you look at when we increase the concentration, our area of the graph is much, much larger. It includes all of this up here. So again, by increasing the concentration, we are increasing the number of molecules that have sufficient or have the activation energy to successfully collide. But we do need to know that this is how you draw the graph for that. So concentration, think about it logically, you're not altering the kinetic energy in any way, but you are increasing the number of molecules in your reaction. The final example we have is the use of a catalyst. Now, the use of a catalyst is a little bit different. We again have number of molecules and kinetic energy, but this time we are going to make the activation energy sit here. And we usually label that with a little E and an A subscript A. So if our activation energy is here, then that means that, as always, this number of molecules here, the area under that graph, represents the molecules which have enough kinetic energy to successfully react or collide. Now, what a catalyst does is it actually does not affect the distribution of this curve at all. If you think about what a catalyst actually does, it provides a surface for reactants to collide with each other with the correct geometry. So what adding a catalyst does to this is it actually moves or alters the activation energy required for the reaction. So rather than it being over here, a catalyst simply lowers it to maybe here. Now, as you can see, where here are the number of molecules that have energy greater than the activation energy. Let's look at it now. All of this area here under this graph is now representing the number of molecules with an energy greater than the activation energy. So what catalysts do is they do not alter the distribution of that curve. They simply lower the activation energy so that more molecules have energy greater than the activation energy. So the activated complex, this is a high energy intermediate state where bonds are both breaking and forming, is shown on what is called potential energy diagrams. You have seen these before when we were talking about enthalpy, but I'll remind you what they look like in just a wee second. But this is the energy barrier that must be overcome when changing reactants into products. So it's right at the top of what I like to call the energy hill. that the particles must get up this hill to get to the other side. Some reactants might get so far up the hill but not have either the correct geometry or the correct activation energy, and they do not turn into products. The activated complex is an area, quite an uncertain area, where not all collisions will be successful. Some will turn into products, but some, of course, will turn into reactants. But most often you're asked a question in the SQA paper about where the activated complex is, and it lies at the top of this energy hill, if you want to call it that. So if you remember from last week's lesson, we were looking at the, I think it was hydrogen bromide example. When the two molecules come together to react, they form that kind of intermediate state. That is what the activated complex is. And like I said, you do need to know where to put that on a diagram, and it is always found at the top of this energy hill. That is the kind of deciding point where the molecules are either going to be brought together successfully to form a product, or they're going to fall back into reactants. So, catalysts. As we've already discussed, what the catalyst does is it allows reactions to be carried out at a lower temperature. Remember, we've just learned it does that by lowering the activation energy. In other words, more molecules, or many more molecules, have energy greater than the activation energy when using a catalyst. So some examples of catalysts that are used in industry that you might want to take a wee note of to use as examples. Two that you should be very familiar with from National 5 are iron, which is used to make ammonia by the Haber process; platinum, used in the manufacture of nitric acid, which is in the Ostwald process. Rhodium and platinum are the two which are used in catalytic converters. Again, something you might be familiar of from S3. And nickel, we are definitely familiar of for more than a few different reasons, to make margarine by hardening vegetable oil. So we learned about that in Unit 2, and I also always talk about it. So choose a couple of them to just have as your examples of catalysts in industry. Now, what you'll be thinking probably is, how does this actually work? What actually happens when we add a catalyst? Well, on the diagram before, which shows the distribution, the number of molecules versus kinetic, you need to be aware that the activation energy is simply a line drawn on that diagram. So it's a line that represents molecules below this line do not have the sufficient activation energy to successfully collide, but molecules after the line do. Now, this is a different diagram altogether. This is a potential energy diagram which shows the reactants forming products. Now, this happens to be an exothermic reaction because, as you'll see, the value of potential energy in the products is less than that of the reactants. So that would be an exothermic reaction. Now, we used to draw these without this little bump. In National 5, we would say, here's the reactants, here's the products, and that the difference is the enthalpy. We're going into this a wee bit more depth now, and we realise that it's not as simple as that. Some of the reactants need to get over this energy hill to form the products in the first place. Now, what a catalyst does is it alters the height of this hill. So I'm going to show you what that looks like. So when we did this at National 5, we would do, here is the value of the products, here is the value of the reactants. To calculate delta H, you would take the difference products minus reactants, and it would give you this value here. So that's delta H, is the difference between those 2 points on the graph. Now, the activation energy can be annotated on this graph as well. Now, the activation energy for the forward reaction is going to be how high that hill is. So how big is the hill is the activation energy. So that's going to be here. So that's activation energy. Okay, so the activation energy is how much energy, so how big is that hill, how much energy do the particles need in order to become products. The enthalpy change, remember, as always, is just the products minus the reactants. So that's the difference between these 2 points here. Now, when we've spoken about this, this is for the forward reaction. So the pink is showing you the forward reaction. I'm going to show you the activation energy of the reverse reaction. So if we think about it, the products are coming along here. They then have a much, much larger energy hill to overcome, if you want to think about it like that. Which makes sense. If you think about any exothermic reaction you can think of, for example, burning a match, how easy is it going to be or how much energy would be required for that match to be unburnt again? So it kind of makes logical sense. The activation energy for the reverse reaction is going to be this height here. So the pink is the forward reaction, the green is the reverse reaction. And you do have to be aware of where these values are on the graph, and also when the graphs have numbers, be able to use those numbers to give a value for the activation the activation energy for the forward reaction, the activation energy for the reverse reaction, and of course your enthalpy change. Now notice it doesn't matter which way the reaction is going, the change in enthalpy will always be this distance here. So if you were asked a question about adding a catalyst and you were given a diagram which says this is the uncatalyzed reaction, draw a line to show the reaction pathway of a catalyzed reaction. This is where you would need to show that the activation energy has lowered in both sides of the reaction. So all you would need to do is your reactants start in the same place, your products finish in the same place, but your activation energy, which is this distance here, remember, has been much lowered. So it's not as high as it used to be. That's what the catalyst does for a potential energy diagram. So potential energy diagram, you are simply lowering the energy hill. Remember, on the other diagram, which is a distribution diagram, you are moving the line backwards. So wee reminder, we recap about enthalpy. You do have notes on this, but if you wanted to take some more, then that's fine. What is enthalpy? Just a wee reminder, it's a measure of how much energy is absorbed or released by a reaction. In the reaction we just discussed a wee second ago, that would be energy released since it was exothermic, but oppositely, if it's endothermic, it would be absorbed. So the delta H is always positive for endothermic reactions and negative for exothermic reactions. So you can almost check your answers with this. If you get a positive value and your graph looks like an exothermic graph, then you've done something wrong. So for an exothermic reaction, just a wee recap of what I said before. So this will be the activation energy for the forward reaction, but delta H is remaining the same. So you're going to do products minus reactants. For an endothermic reaction, if you look here, the activation energy is much larger. And the delta H, again, still the same distance. It's the distance between the straight line of the products and the straight line of the reactants. The best way to get your head around this, because it is quite an abstract concept, it's very difficult to imagine these molecules in your head behaving this way. It's hard to have a really good understanding of the graphs unless you do practice. So we're going to work through these questions. As always, I hope that you will attempt the questions first of all and then check your answers and self-mark using the video. So we have a reaction here which has the following potential energy diagram. So you can recognise the potential energy diagrams because they say potential energy. And it's asking us what the activation energy for the forward reaction is. Now, if we in our minds say to ourselves, right, the activation energy for the forward reaction is the energy hill that the molecules must get over. That immediately says to me, here it is here. It's this section of the graph here. Now this is a multiple choice question where we have all of these values which are not numerical, they are in letters. But if we wanted to find the value here between x and y, we would just take y away from x. So for example, if we put some numbers here, say this is 25, say this is 100, and this is 80. If we took y away from x, so 80 away from 100, that would give us a difference of 20, and that would mean our activation energy was 20. So the answer to this is A, which is y being taken away from x. Okay, number 2, the rate of reaction can also be altered by changing the temperature or using a catalyst. Graph 1 shows the distribution of kinetic energies of molecules in a gas at 100 degrees C. So do we see how these graphs are different? This graph is the distribution of kinetic energies of all the different numbers of molecules, and it will tell you on it that it has number of molecules and kinetic energy. Now this is saying graph 1 represents 100 degrees C. Add a second curve to graph 1 to show the distribution of kinetic energies at 50 degrees C. So we are being asked, what does the graph look like if we lower the temperature? So we're not increasing the temperature, we are lowering the temperature. So if this graph 1 is quite spread out to the right hand side, what we want to do is we want to make it taller and we want to push it towards the left. So that would look something like this. Now again, if we were to have a look at where the activation energy would lie, say it was here, that would mean, and it makes sense, that graph 1 at 100 degrees would have many, many, many more molecules with energies above the activation energy, whereas our lower temperature, which is the one we've just drawn at 50, would only have this very small portion here of molecules with energy above the kinetic energy, the activation energy, sorry, to react. Part 2 of this question says in graph 2, the shaded area represents the number of molecules with the required activation energy. So here we have our little activation energy here. Draw a line to show how a catalyst affects the activation energy. Now this can be a tricky question, and the reason being is that we know a catalyst lowers the activation energy. Now what people get confused with is the different graphs that you can show this on. This happens to be a kinetic energy distribution graph, which means that the activation energy is simply a line. So what we need to do is we need to draw the line at a lower point in the graph to show the activation energy being lowered. So you could draw the activation energy anywhere on the x-axis. I'm going to draw it here. And I would always just label it just in case. But anywhere that is to the left of where the activation energy already is going to get you the marks for this. Now remember, you can also be asked about how a catalyst will affect the activation energy on a potential energy diagram, but I'll show you what that looks like in a wee second. So just while we're talking about it, here is what the catalyst does on the potential energy diagram. So as you can see, the straight line here is the uncatalyzed reaction. The dotted line is the catalyzed reaction. Why? Because the straight line must be the uncatalyzed reaction because it has a higher activation energy. Remember, the activation energy on a potential energy diagram is this energy hill that the particles need to get over in order to make products. We can see this dotted line has a much shorter energy hill, which means that the activation energy for the forward reaction has been lowered. What the question is asking is what is the enthalpy change for the catalyzed reaction? Now, in this example, when we're asked for the enthalpy change doesn't have anything to do with the activation energy. I just wanted to show you that while we were talking about it a wee second ago. So the enthalpy change is always products minus reactants. So our products here are at 50, our reactants are at 100. So 50 take away 100 is minus 50. So that is going to be answer B. So the catalyzed reaction does not affect the enthalpy at all. The enthalpy is the difference between the straight line of the products and the straight horizontal line of the reactants. If it asked us the activation energy for the uncatalyzed reaction, just while we're here, it would be this part here, take away this part here, which would be 200 take away 100, and that would be 100. The catalyzed reaction is only half that size. So it goes from here to here. So from 100 to 150 would be 50. Hopefully you can see that really clearly. Okay, so last question here is probably the most complicated. It combines a lot of different questions. State the term for the unstable arrangement of atoms. So what do we call the part at the top of the energy hill? Well, we call it the activated complex. So that is the answer to part A. Activated complex. Calculate the enthalpy change in kilojoules for the forward reaction. So the enthalpy change for the forward reaction, remember enthalpy is always the same. It is the straight horizontal line of the products, take away the straight horizontal line of the reactants. Now you might be looking at this graph and thinking there are no numbers on the scale. But that's okay because we're given the activation energy for the forward and the activation energy for the backwards reaction. Now this is a problem solving type question where it requires you to be able to look at that graph and say, right, the difference between the energy hills on both sides will give me that gap between the straight lines that I'm going to try and draw on this with a straight line, but it could be messy. Okay, so see this gap here? That is what we are looking to calculate the value of. So if from this part here up is 182.8 and this part here up is 173.2, then all we have to do is take the difference between those numbers to give us the value of that gap. So it's going to be 182.8 take away 173.2, and that is going to give us 9.6. Now, be wary that even though that gives us 9.6, that's given us the difference between those two numbers. So it's given us the value of that little gap here. But what we need to bear in mind is that this is an exothermic reaction. So this is a kind of hidden trap in this question. The value for the products is lower than the reactants. So that means that we're going to need to put a negative in front of that. So it's going to be negative 9.6 kilojoules. Part C is the last question. Platinum can be used as a catalyst for this reaction. State the effect that platinum would have on the activation energy for this reaction. All you have to say for this is that the activation energy would be lowered. It doesn't ask you to draw on the graph or anything, but I suppose you might get asked one of those questions. So all you would do was draw the same lines ending and starting in the same place. I've made that a wee bit messy. But ending and starting in the same place, just with a lower activation energy in the middle. So, our learning intention for today was to investigate some of the chemistry behind reactions by taking a look at activation energy and enthalpy in more detail. I think you'll agree that it is in quite a lot of depth, and you do need to be able to understand the terms kinetic energy, activated complex. So what you really need to do is sit down with your notes and try and puzzle this out for the next wee while. What you do need to be able to do is define activation energy and the activated complex. You also need to be able to show on a graph where the activated complex is and show your understanding of what all these terms mean by annotating the graphs. So the graph with the distribution for temperature, concentration, and catalyst you need to know off by heart. So I really hope that you've been able to annotate those successfully in your notes. Hopefully by answering questions you'll have no problems with it and you'll all get on okay with the questions. If you have any questions about this lesson or any of the work that's been posted this week, then as always you can chat to your teacher on Google Classroom. Hope you have a good week.